Good evening, everyone. Welcome to today's KWK talk. To welcome all the audience formally and also to introduce the speaker, I call upon our director, Dr. B.R. Guru Prasad, sir.
Respected speaker of today, Professor Malabika Pramanik, ladies and gentlemen, and good afternoon to all of you. Welcome you all. I welcome you all to this yet another lecture under the Kaapi with Curiosity program, jointly hosted by ICTS and JNP. And today we have a very interesting topic about numbers. Okay. And, the thing is, I can't help numbers, are they normal? The Honorable Professor asked this question in the topic. She has given this topic. She says, normal people are the ones who are not known very well. It is like, seeing the sun in the sky. Every day, sun will be there. Okay. At the same time, extending this to the domain of numbers, how do we define it? It is not for me to preempt the lecture, so that she is going to talk about it. And I'm sure it will be very interesting. And whatever she has told in this, what impressed me was, okay, she will discuss in this lecture some interesting facts about normal numbers and connect those aspects to a few seemingly unrelated areas of mathematical sciences. There lies the crux of the lecture. I'm sure it would be interesting. And let me say a few words about the speaker. Professor Malabika Pramanik is a professor of mathematics at the University of British Columbia at Vancouver. And of course, she is the scientific director of Banff International Research Station. She obtained her, she's an alumnus of Indian Statistical Institute. In a lighter vein, ISI was Indian Statistical Institute. Once upon a time, everybody knew. Now ISI means something else. ISI has become ubiquitous now for a different reason, that acronym, not acronym, abbreviation, okay? So, and she, of course, being an alumnus of Indian Statistical Institute, ISI, she later received her PhD from the University of California at Berkeley in 2001. And before joining University of California at Berkeley, Dr. Pramanik held positions at the University of Wisconsin, and it is at Rochester, New York, and again, California Institute of Technology. Professor Malabika Pramanik's research interests cover harmonic analysis, geometric measure theory, and complex variables. She has received 2 UBC Killam Awards. Naturally, so many awards and accolades have been given to her. And Ruth E. Mishler Memorial Prize. Of course, the prestigious Canadian Mathematical Society's Krieger Nelson Prize for Research Excellence, and amongst others, many of them. One more interesting thing is she's an advocate for equality, diversity, and inclusion in STEM fields. So I had the pleasant task of introducing Professor Pramanik. Now I will hand over the mic to her. Ma'am, please.
Before that, I would request our director to hand over a memento from ICTS side to the speaker. Madam, if you can please accept this.
Hi, everyone. Good evening, good afternoon. And how are you today? Okay. So thank you all for showing up to this talk on this nice winter afternoon on a Thursday. I really appreciate the time that you have spent coming here. And I'm hoping that in this audience, we can have a chat about, of course, what's in the title, numbers, but more generally, mathematics, what it is as a pursuit, what it is as a profession, and make this an interactive session more than a lecture. Is that okay? All right, good. So let me start with, so this is the title of my talk. So what are my short-term goals in this talk? I'll start by just doing a little lazy foray into the number system with the goal of telling you midway through the talk what a normal number is, why they are called normal, and why should we care about them. That's the goal. Okay. So let me start this off with a question. What is the first number you know of? Absolute first number. One? You are, yes, well, I think there's something that came even before one. 0. And this one, we Indians can lay claim to because ancient India has the undisputed right on this number, at least the legend has it that Brahmagupta is the one who talked about 0 first, and there were mathematicians from the Arab world who just spread it to the West and so on, but 0 is the first number. Okay. Once we have 0, there is the others, just starting to count by the fingers, we end up getting numbers like 0, 1, 2, 3, and so on. And these numbers collectively have a name. What are they called? Say that again. Whole numbers? Yes. So these are called the whole numbers. Very good. Thank you. Sometimes they are also called, these are examples of integers or non-negative integers. Once you have these non-negative integers, what are the next numbers that you learn? Say that again. Negative numbers. What are those? Give me some examples. Okay, so once you have 0, 1, 2 going this way, on the other side, you have the negative numbers, -1, -2, -3, and so on. And these are called the negative integers. Perfect. Do numbers stop there? Are there any more? Okay. There are, yes, go ahead.
Yeah, there are fractions and decimals which are in between these.
There are fractions and decimals that are in between these, and this is exactly what I would like to sort of try to clarify a bit more. So let me draw a line here. This is, say, 0. This is 1. This is 2. This is -1, and so on. Give me a number. Write the natural progression from after integers are a certain kind of numbers. What are they called? Real numbers? You have actually skipped a couple steps ahead. Between integers and the real numbers, there is rational numbers. Thank you. These are very important, especially if you are trying to have a pizza and you don't want a whole pizza, you want a fraction, you only want 1/6 of it, then it's important to talk about fractions, which are also called rationals. So let me try to write this here. So let's say things like 2/3, -3/5, these are called, in general, if you have m over n and mn are, this is non-zero, and this is a whole number, an integer, these are called fractions. Or fractions. So really, if you look at this progression, it's like if you have played with Lego, we have building blocks, which are the integers, and we play around with these integers to create numbers with greater complexity. Okay. All right, so now let's say we have like if numbers like 1/2, 4/3, and so on. What is the next type of numbers that we learn about? Real numbers?
Irrational.
Irrational numbers. Great. So let's move on here. Now, here's my question, and this is somehow is going to lie at the heart of this talk. When we talk about irrational numbers, how are they defined? How are they created? Rational numbers are created by looking at the quotient of one integer upon another. How are irrational numbers created? Any examples of irrational numbers that pop into mind? Pi and Euler's constant.
The square root of a non-square number.
Okay, great. So we have some examples. So let's start with the examples. So the examples, thank you all for chipping in. So examples that I got are, let's say, square root of, like square root of 2, like pi, like e, gamma, the Euler's constant, as you said. So these are all, let's just stick with square root of e and pi because these are probably the most naturally, frequently occurring. But right now, as I have written them, they are just symbols. What are they?
We are not able to represent them as fractions. So for example, I think E comes from, I don't know, calculus. Root 2 comes from Pythagorean,
Yeah.
pi circle something.
That's right. So, exactly. So you have kind of hit the nail on the head that these numbers come up naturally. We know that they are not rational, but neither do we have a clear description of what they are, because what would happen if we tried to write them down in decimal expansion?
Terminating decimal expansion.
They have a non-terminating decimal, not just non-terminating, that's 2 of 4, but also non-recurring. So irrationals lie on the real line but unlike rationals, their decimal expansions are non-terminating and non-recurring. Okay. Great. So at least we have some description of what an irrational number might look like. But in the process of writing down this description, we have used a word which is going to be key in the rest of this talk. And I'm going to highlight this. So there is this word that showed up called decimal expansions. What exactly is a decimal expansion? We are going to spend a lot of time today understanding expansion. What is a decimal expansion of a number?
Yeah, when you divide the number using the regular division, long division method, whatever you get as the quotient is the decimal expansion.
Okay, so let's write this for it. Let's also do an example of a decimal expansion. So if we want to look at the number, say, x equals 0.1812, we can think of this as just as you said, it's like 1 over 10 plus 2 over 100, or 2 over 10 squared, and geometrically it has a meaning. So at the first stage, you take the unit interval 0 to 1, you break it up into 10 equal pieces. So this is the point 1 over 10, 2 over 10, 3 over 10, and so on. And we know that this point lies somewhere here. That's this first step. Okay? At the next step, the fact that it's 2 over 100, where does that come in? Well, we take this interval and let's magnify that interval. This is 0.1 and this is 0.2, and we break this into 10 equal pieces, and the second one over here becomes 0.12. So a decimal expansion is somehow related to iteratively decomposing an interval into 10 equal pieces every time, and then determining in which sub-interval or sub-interval that the point x lies. Okay? So every x really has a range. Okay, let's see now. So every point x, if you take 0.1, 0 to 1, and then you take a little bit of an interval, this is of length 1 over 10, and then you take another interval inside it, which is of length 1 over 100, and inside it you look at a tiny one, which is of length 1 over 1,000. Every real number between 0 and 1 is going to go into one of these, and it's going to create an array. And if you can stop at a certain point, or you can keep going, and at the end of it, you are going to reach your real number x. With me? Okay. Now, my question to you is, what's special about 10? So I wrote this as a decimal expansion. Of course, decimal has to do with the number 10. What is so special about 10? We have 10 fingers. Exactly. That's right. Because God gave us 10 fingers, they are easy to count on our fingers, and that's why 10. But from a mathematical perspective, there is absolutely no reason to choose the number 10 over any other integer. Okay? So that's going to take me to my first definition today. All right, so pick any integer b greater than or equal to 2, that I claim that any real number x can be written as, and in fact, to keep life simple, I'm just going to pick an x that is between 0 and 1. Any number x that belongs to the interval 0 to 1. Maybe you are familiar with this notation already, but if not, it just means x lies in the interval 0 to 1. Can be written as so it can be written as this potentially infinite sum x1 over b plus x2 over b squared plus x3 over b cubed and so on. It is exactly like this expansion that you see here, but the base is no longer 10, it's b. Hang on. Okay, let's give this one more try. All right. We can write it this way, where these objects, x1, x2, x3, these are called the digits of x in this expansion. So this kind of an expansion has a name. This is called the expansion of x in base d. And these numbers, x1, x2, x3, these are called the digits of x. Okay. So I have a question for you. In the decimal expansion, when we write x in this way, what are the possible values that a digit can take in the decimal expansion?
0 and
Very good. 0 to 9. So the only possible digits here are 0 to 9. So by sort of transference then, if x1, x2, x3 are the digits of x in the expansion with respect to base b, what are the possible values of the digits x1, x2, x3? 0 to b minus 1. Very good. So these can take values in 0 to b minus 1, and I'm going to call this z mod b. Okay, now let's do a quick example to kind of get warmed up before I throw another. I'm going to give you a couple of numbers, and you tell me what their digits are in different expansions, okay? So let's say x is the fraction 1/3. If the base is 10, what are the digits of x, of this x? Sorry? 0 and is 0, well, if it's y 0, just 3, right? Oh, 0 point. But remember, because it's between 0 and 1, I'm only starting after the decimal. So the 1, 0 before the decimal, I'm not counting. So just 3. Very good. So x1, x2, x3, and so on, then everything inside is 3. If the base is of expansion is 10. Suppose the base of the expansion is 3. What are the digits? x1 is 1. What about the others? Great. x1 is 1, x2, x3, x4, they're all 0. Okay. Last one. Suppose I change the base yet again. And this time, the base is 4. What are the digits of x? All ones. Excellent. How did you get that?
I just use the formula for geometric progression.
Yes, very good. Excellent answer. So let me work that out. So what you meant is you looked at this geometric progression, 1 over 4 plus 1 over 4 squared plus 1 over 4 cubed. This is a geometric progression with common ratio 1/4. So there is a formula for what it's going to be. It's 1 over 1 minus a quarter, and times a quarter, because that's the first term. And once you calculate this out, this is 1/3. So this expansion says that these numbers, this is 1 over 4, this is 1 over 4 squared. So this is x1, this is x2, 1 is x3, and so on. So in this situation, x1, x2, x3 are all these. Okay. But you can understand that if I suddenly throw a completely weird number at you, like 15 over 87, and a completely ridiculous base like 73, it's not really easy to find what these different digits will be, although of course there are digits, right? Okay. So as you can see, the same number admits different expansions in different bases, and in this vast area of number theory, which is a really vibrant area in pure math, a lot of time is devoted to understanding how these different expansions of the same number in different bases are related to each other. Okay? Now, I think I should somehow make an attempt to describe what normalcy means. Okay? When do you call a person normal? Maybe that's a loaded question. When is a human being normal, folks? I realize this is not a math question, so more of a philosophical question. When is a human being normal?
When they're doing what you expect them to do.
Yes, thank you. So that's a great answer. So the answer to the question, when do you call a person normal, is when they do what you expect them to do. When they sort of respond in a manner that seems fair, neutral, and impartial. And I could not have expected a better response, because that's exactly what we are going to call a number normal also. Okay? When they do what you expect them to do. Okay. All right. So let's remind ourselves that we are looking at an expansion of this type. And these are the digits. I'm going to say that x is normal if it does not show any bias toward any of the digits in its expansion. It treats all the digit expansions in this base B fairly. Okay? Now that's treating somebody fairly, again, is not a math term, but I claim you can make it into a math term. In a decimal expansion, when do you call a decimal expansion fair?
to it?
Sorry?
When there is a pattern to it?
When there is a pattern to it, is that fair? Because I could say, look at the points, 0.11111111. It's a pattern, it never changes, it's flat. Is it fair? It's not paying any attention to the other digits, 2, 3, 4, and 5. So, random? What does random mean?
Any digit out of 0 to 9 or from the base
Yes.
b minus 1,
Yes.
and there could be any the probability of picking each of those
Yes.
should be equal. That is 1 divided by b minus 1 should be the probability of picking each one of those digits.
Well, that is true, but you see, this number, it's not being picked. It's already handed to you. Okay, it's already given to you, and I need to figure out and this b has also been given to you. How do I determine if this distribution of digits is fair or not? If I let you pick randomly, what you said makes perfect sense, but I'm not letting you pick. I'm handing you this number. So, what's fair? All the digits are represented. Okay. Now, I think that's a great place to start. Let's do that. So let's take a decimal expansion. So x is 0.1234, 0.01234 all the way up to 9. So this is a decimal expansion in which all digits are represented. Certainly it is more fair than, let's say, 0.11111. Is it truly fair? It is.
Interchanged, but then
Positions can be interchanged. So if you like, you can also choose 0.098, etc. all the from 2, 1. Okay, that's also. So you folks should be more critical, not just number-wise, but even societally. Because if you tell everybody this is fair, I claim this is not fair. You should be more critical of numbers and of other phenomena too. Why is this not truly fair? It's fairer than other things, but not truly fair. Why?
It's biased towards 0. 'Cause
Yes, it
Yeah,
is
okay.
biased with 0 because everything after this is 0. So if you stand back and look at the entire decimal expansion as a whole, 0 is overwhelmingly present. And in the limit, the frequency of zeros takes over. The frequency of 1 up to 9 becomes 0 in the long run, and the frequency of zeros becomes 1. This is entirely biased towards 0. That's why it's not fair.
9 with a line on top, like recurring.
Okay, good. At least that's much better. So this 0.012 up to 9 recurrence is a better. I'll call this is fair in the sense that every digit occurs in X with the same limiting frequency. Okay. So we are going to call such numbers with this property simply be normal. So this is going to be one of the words that I want you to sort of take home today. We are going to call such a number when every digit occurs with the same limiting frequency. Such numbers are called simply be normal. Let's continue our pursuit of normality, okay, or fairness. I agree that in the sense of every digit occurring in the digit expansion, yes, this is quite fair. You can keep going to the end and every digit will occur with the same limiting frequency. But I claim if I want to hold numbers to even higher standards, even this is not technically the best possible. We can do better. What is the better criterion of a fair number or a number which is even more normal? Ideas?
In every base.
Sorry?
In every base.
In every base? That's a great answer. Let's take that answer. So we are going to call that there is an actual, in fact, I'm going to get there. Let's, for the moment, let's call X is simply normal. If it is simply be normal in every case. Okay. Usually when we write such things and ask for such criteria, as mathematicians, as budding mathematicians, you should ask certain questions. I make a definition. What's the next thing to ask? Is there an example? I could say, if suddenly it turns out that there are no simply normal numbers, all this discussion is moot, right? So if anything, I would have to convince you that such numbers exist. Okay, otherwise there's no point. I'm going to set that aside for a little while and continue to talk about normality a little bit more. I claim that there are certain features in that this number does not capture. Okay? And I would like a truly fair number to actually get to that higher ideal that this X doesn't reach. What is such a criterion?
Random.
Well, yes, the word random has come up a few times, but what does it mean exactly? In concrete terms, what does it mean?
Basically ordering. So if I'm thinking that if I only pick first 3 digits, then in chunks of like or multiples of 3 probability of like, for example, first 3 will have more ones.
Yes.
First 12 will have more ones than maybe 9s.
Okay.
So it's something like that.
Okay.
So maybe I will take all permutations of 0 to 9, arrange them and then put a bar over it.
I see. Okay. I think, yes, that's right. That would be a better definition of normality. So let me try to rephrase what you said. If I understood correctly, part of this, the complaint with this expansion is that suppose I want the pair 3, 5, this pair to appear in this digit expansion. Does the pair 3, 5 appear consecutively ever? Well, it doesn't. 3 is always followed by 4 and preceded by 2. That's not fair. And as you said, what we want is not just every digit to occur with the same limiting frequency, but every pair of digits to occur with the same limiting frequency. And by taking that further, for every k, that was your point about permutations, take any k long sequence of digits. Every such sequence must occur in the limit with the same limiting frequency. So I'm going to write that down. So say that X is B normal So this is kind of a mathy, but I promise you this is the only mathy notation that I'm going to use. For any k and any sequence of digits d1 through dk in z mod b to the k. If you this, I have to explain to you what the same limiting frequency means. What it means is the following. Look at the proportion of the first capital N digits, where xi is d1, xi plus 1 is d2, xi plus k minus 1 is dk. So this sequence d1 through dk occurs consecutively. Every time that happens, you pick that I and you ask that in the limit, it's the same for every choice. So you tell me, what should this limit be if it has to be the same for everything? No, for a fixed k. For a fixed k, how many choices of k long digits do I have? B power k. So if they're all going to be equal, what should this limit be? 1 over b to the power of k. Very good. Thank you. So this is what you want in the limit. So this is called a b normal, and x is absolutely b normal. So x is absolutely normal. If it is normal if it is b normal for every b. For all. So this is going to be our notion of normality. Okay? So this is about as far as we can push the notion of fairness. So say that again.
The difference between this and this, what is it?
This one is simply b normal. The word simply. We only care about single digits. Here, the distinction is we care about not just single digits, pairs of digits, triple subdigits, quadruple subdigits, in fact, all permutation for every scale. It's a much, much stronger criterion than this one. All right. So there are two things that I want to do before I wrap up. First of all, are these things even there? That's the first question, because otherwise I would have wasted your time. And number two, if they do exist, are they good for anything? Is there any point to studying these objects? Because if there isn't, well, again, I have somewhat wasted your time. So, the first result that I wanted to tell you about this, people were very, very interested in this for a very long time, long before computers and things came along. They wanted to study the nature of numbers. And you may be surprised that one of the first important results in this subject dates back to 1909, okay? More than 100 years ago, due to a very famous mathematician by the name of Emile Borel, okay? And I'll state what he found. What he found is that, and I'll put this in quotes because I may not have, so we are going to take this apart. He showed that almost every real number is absolutely not. Okay? I know you have questions, so maybe I'll let you ask what the question is. Okay, would you hand him the microphone, please, because that was a great question.
We just found so many numbers which were not absolutely normal.
Exactly. So what exactly was Borel thinking? We started this discussion by creating like half a dozen numbers that are not even simply normal. So how can almost every number be absolutely normal? You see, there is a little bit of a mystery that hiding in this word almost. Almost does not mean all, okay? And almost just means that there can be many numbers which contradict this statement, but the numbers that do obey this are overwhelmingly more popular. That's what it means. And I'm going to try to make this precise in a moment. What does almost every mean? So almost every in particular means that take any interval a to b on the real line, and you try to pick out the numbers here that are absolutely normal. So one consequence, if you look at the length or the size of absolutely normal numbers, in a to b, that is actually b minus a, which is the full length of this interval. And in fact, the length of, sometimes this is called measure, this is the size of not absolutely normal numbers in a to b, is actually, and you can, being 0 doesn't mean that this set is empty. All rational numbers are not absolutely normal. Rational numbers are infinite in number, but they are the number of rationals in this interval, even though they are infinite, is far, far less than the number of absolutely normal. Okay? So there is this notion, this rather mystifying notion of largeness that's hiding under this word almost. For those of you who are going to go on to higher level math, this is sort of kind of the crux of this area called measure theory, which tells you how to measure the size of a set, what is large and what is small. So at least I have convinced you that we are not in vacuum. Devdatta, how much time do I have? We have 20 minutes? Okay, great. So let me stop for a couple of minutes to see if you have any questions. Yes. Yes. In fact, this word almost, these statements are actually part of this definition of Lebesgue almost. So this is a rigorous statement. Yes. This is actually part of Borel's original. Yes. Yes.
Not a limit or
Not a
nearly
limit.
equal.
No.
Is equal have a meaning from what we
No,
normally
doesn't have a different meaning. So just to give you an example, let's do a little thought experiment. It's exactly the way that we understand equality. Okay, so let's do an example. So suppose we take an interval 0 to 1, and what is the length of this interval? 1. Good. So length is 1. Now suppose we take a number here, just the point half, and I throw it out. So now I have 0 to 1, 0 closed, half open, and then half open 1. Okay, so it's the union of two disjoint intervals. What's the length of that interval? I know you know the answer to this. What's the length of that interval, or those two intervals put together? You want to say nearly 1, but is it nearly 1 or is it exactly 1? Can it possibly be smaller than 1? That's right. A point has no length. No, a length is a measure. So if you actually take a tape measure cannot measure a point. To a tape measure, a point and back and like nothing are identical. It cannot distinguish It doesn't mean that a point and an empty set are the same. It is just the length, our way of measuring is not fine enough to pick up the existence of a single point,
Points can I take out so that it is less than 1?
at least countably many. You can take out all rational points and the length would remain 1.
What if you take out the irrational points as well? Then it will also be 1, right?
No, that's exactly when it's not true. So length of this is still 1. And if you can take out all the rationals, it's 1. But if you take out all the irrationals, you would get 0. Because irrationals are by far much, much more abundant on the real line. Irrationals have length, full length. Rationals have length 0. Okay? All right.
There is a question in the YouTube chat. And
Yes.
I would like to read that from Anthony Soprano. So you're pointing to irrational numbers, I guess, but are they all equally fair? Are normal fair numbers by definition a subset of real numbers? So because it was related to this.
No, I think it's an excellent question. So are all irrational numbers fair? I'm going to write this question down kind of because it is in a sense that in the mathematical world, it's the question of the century. So are all irrational numbers The answer is no. Not all irrational numbers are fair, but by the same token, we don't know which ones are. Okay? I'm going to give you an example. So this is a really big open question which have like stood open in the field probably for more than 100 years now. We don't know even if what are the most basic irrational numbers we know? We talked about them. Pi and root 2, we don't know. We don't know if they are absolutely normal or not, if they are fair or not.
How do you know that all rational numbers are not fair?
Because they have been constructed. So I was going to sort of tell you why, how in a moment. So I'm going to explain that to you in a moment. So for example, we do not, but we still do not know if irrationals like root 2, pi, etc. Are absolutely normal. Okay. When I say that are all irrational numbers fair, and I said that the answer is no, that's because people by hand have actually created numbers for which they have been able to show fairness or unfairness. And I'll end the mathematical part of the talk here by giving you a couple of examples.
Also on that note, Professor Pramanik, somebody is asking what about removal of rationals and algebraics but leaving the transcendentals?
And what about it? After we do that, then what?
Yeah. What about that?
Well, you can remove the algebraic numbers. You can remove the rationals. What is left is there's the collection of transcendental numbers, but we don't. It's not true that all transcendental numbers are absolutely normal. When I said no, this is actually the work of my UBC colleague Greg Martin, and if you should look up his paper in American Math Monthly, he creates a transcendental number which is actually not normal in any base. Okay? So there are such numbers. Here is another number, 0.1234, all the way up to 9, and then 10, 11, all the way up to 99. So basically, all I'm doing is I'm creating a decimal expansion by linking up all the natural numbers, okay? This number is actually known as Champernowne's constant, after the person who discovered this result. And this is known to be absolutely normal, sorry, not absolutely normal, normal in base 10. Similarly, if you look at, tell you or at least discuss why on earth we should study these numbers, and I haven't told you, right? Can you guess? Can you guess why this might be a worthwhile avenue of study?
Is it to generate more difficult rules of finding numbers? Or, I mean, we can know such
That
things.
is definitely the real reason behind Borel's original result and follow-up. Borel was extremely interested in the properties of numbers, in the arithmetic and statistical properties of real numbers. So pure mathematicians, the theoreticians, have always been very interested in, so these numbers like integers, rational, irrationals, we think of them as God-given. We don't doubt them. But what is really their distribution and their structure? And mathematicians have been scratching their heads for centuries trying to really understand that in depth. So what you said, finding more complex and intricate tools for understanding the real number system is originally what drove this problem. Sort of fast-tracking it to this day and age, why is this still relevant? Should such studies be relevant?
Cryptography.
Say that again.
Cryptography.
Cryptography could be one. You could use a particular sequences of digits to create certain numbers. Yes, absolutely. That's one place where sort of blocks of digits of numbers has applications. It has tremendous applications in this area of computer science called algorithms. Okay? We may not be able to write out sort of what an absolutely normal number looks like, but you must have run into codes which requires the generation of a random number or of a password that is truly random, whatever that means. You have told me this word random a couple of times during this lecture. So if you are trying to generate a number that is truly random, you cannot get any more random than an absolutely normal number. It is random in the purest, strongest form of the word. It is extremely sort of comforting to know that almost all numbers are absolutely normal. I mean, I hope that's true also in human life, that almost all people are absolutely normal. But let's pair this with the fact that absolutely normal numbers still remain tantalizingly out of reach. And nobody up until now has been able to find a single example of an absolutely normal number, even though Borel's theorem from more than 100 years ago says they are everywhere around us.
How did he say that theorem then? Or some construction?
No, in mathematics, there are proofs that are existential, which tell you certain things exist without actually being able to provide you a single concrete example. Borel's theorem is in that category. It gives you moral support. It doesn't give you an actual number. Not But the fact that he says not only are there numbers that are absolutely normal, the fact they're almost everywhere. Like every interval has thousands upon uncountably many of them. That's an amazing statement. rendered even more amazing by the fact that in the 100 plus years since Borel, nobody has been able to find a single example of one. So mathematically, it's an important problem. From computer science perspective, even though we have not been able to find an exact absolutely normal number, there are tons and tons of algorithms which try to create the first capital N digits of an absolutely normal number. And this is extremely important in neural networks, in algorithms. Okay, so this is another reason for studying.
If nobody has been able to construct an absolutely normal number, then the proof is a non-constructive proof. So did it use the axiom of choice and?
No, no. It did not use the axiom of choice. It was based on measured theory. It was not like predicated on any axioms. It is just non-constructive. It does not give you a method for creating an absolutely normal number.
Normal, like almost close to our absolute normal numbers.
Right.
Are there some sort?
Yes. So as you can guess, this kind of discussion is the tip of an iceberg. Okay. You can ask all sorts of complicated questions, such as, suppose you have a set B, which is 2, 3, and another set B prime, which is, say, 5, 7. You could ask, or in fact, let's say here, in fact, I'm going to take your question and try to make that work. So let's say B prime is 2 and B is 3, 4, 5, everything other than 2. So when you say almost absolutely normal number, I could interpret that as, are there numbers that are normal in all these bases, but not normal in this base? That's like a definition of an almost absolutely normal number. It just fails for only one. The answer is, there are many such numbers. We know that such numbers exist. Cannot create one. Yeah, sorry. There are many, in fact, because you are in the area. The Hausdorff dimension of such numbers is 1. Ooh, yes. Say that again.
Can you please repeat the last statement? I could hear it clearly.
Hear it clearly? Okay. So let me try to write down. So there are uncountably many numbers x that are normal in the bases B and not normal in B prime, for this B and B prime. So there are many such numbers, and what Rani was asking is, what does many just uncountably many is of course one term. There are other notions of size, different from length, different from counting, and a notion of such thing is called dimension. So the dimension of such numbers is 1. That's what I was telling you.
I have another question. Yes. So suppose we consider the interval 0 to 1, including both the extreme values. So there are infinite numbers in that interval.
Yes.
That can be considered as one universe
Yes.
of numbers.
Yes.
And suppose we consider the numbers from 0 to infinity.
Yes.
That is also another set of numbers which has infinite number of numbers.
Correct.
Which is the bigger among the two?
So this is a very excellent question. The key to the answer lies in the how we interpret the word bigger. If you try to say, is the set of numbers between 0 to 1 larger or smaller than the set of numbers between 0 to infinity? Of course, it's a strict subset. In that sense, the set of 0 to infinity is a bigger set because it contains more numbers. Another way of interpreting the same question is, do they have the same cardinality? Cardinality means, can you find a 1-1 onto mapping from all the numbers in 0 to 1 to all the numbers in 0 to infinity? And surprisingly, the answer there is yes. even though, of course, visually we know that 0 to infinity contains many more numbers. It is possible to create a 1-1 onto mapping, 1-to-1 correspondence exhaustively that takes the numbers in 0 to 1 and maps it in an onto fashion to 0 to infinity. They both have the same cardinality. And in that sense, none is bigger than none. So the key to asking these questions whenever we say bigger or smaller is to nail down which mathematical definition you are using to say bigger or larger, and bigger or smaller, and that will determine your answer.
Yeah, so a thought came to my mind, and maybe you can just give me some. So same argument, but for 0 to 1 and 0 to 2.
Yes.
But if I say another statement, which is I can find a mapping such that some numbers are missed. For example, if I say x is equal to x, then 0 to 1 will map to 0 to 1.
Yes.
But then some number are getting missed, right? Like 1.1 is getting missed. If my mapping is x is equal to x.
Correct.
So if I am defining mapping this way,
Yes.
then I can say they are not equal. What is wrong with?
Well, no. So you see, I can always maliciously define a function which will not have a certain property. For example, if we take the interval -1 to 1 and just say I want to look at the map x goes to x squared, then -1 to 1 will simply map to 0 to 1, right? And it's not really, it's treating the left side and the right side of 0 in the same way. Okay? And you can, in your example, if you just say 0 to 1 to 0 to 2 and your map is x goes to x, then the entire 1 to 2 gets missed out. Okay. No problem with that. But you picked the function. If you are somehow tied to that function, nothing can be done. But the definition says if there exists a function 1-1 onto, which takes this set and maps it completely onto the other set, that's when we say that they have the same cardinality. So it predicates on the existence of function, not the one that you chose, maybe not the one that I chose, maybe we'll both fail, but there may still exist such a function, and as long as that's there, the cardinality is the same.
In such a way, basically.
That is how the cardinality has been mathematically defined in the literature.
Like, who don't know the definition can confuse the term size with cardinality or length with that term cardinality.
Right.
How it is.
That's right. So the mathematical definition of cardinality is that one should be able to find a bijective mapping between the two sets. Yes. Not that every bijective mapping will have this, every mapping will have this bijective property, but there should exist at least one.
So you said that there is no proof if numbers like pi or square root 2, if they are normal or non-normal. So if we take a sort of brute force experimental approach, let's consider first 500 digits of the expansion, then 1,000 digits, then 2,000 digits, and then count the distribution of digits. Proceeding this way, can one get any useful clue to the answer?
I think this has been done. With the advent of new technology and more powerful computing tools, and especially that pi now has been computed to who knows how many millions or billions of digits. It has been checked, normality has been checked, and the folklore belief based on these computations is that both root 2 and square root 2 and pi should be absolutely normal. Based on the computations done so far, nothing indicates to the contrary. But they remain computations at best and not theoretical proofs. A theoretical proof would need an argument that nothing goes wrong after the billionth decimal point, which is still possible. Unlikely, I agree, but still possible. And that has not been shown.
I'll just read one. What makes the question of determining whether pi is normal hard versus that of Champernoun's number?
Yes.
After all, we have very good algorithms to generate digits of decimal expansion of pi.
Yes. So, as I understand it, I am not a computer scientist. Okay, let's first understand what makes the problem different between pi and Champernowne's constant. Pi came about at the time of the ancient Greeks. It has a very concrete geometric meaning. It is the ratio of the circumference of a circle to its diameter. That is how pi was defined. Long, long ago, long before Borel came into the picture. Okay. So the digits of pi were there, and even now we have algorithms to generate digits of pi. But if we do not know, we do not have a formula that tells us exactly what the nth digit of pi in the decimal expansion or in the b-adic expansion is going to be. If I am interested in it, the algorithm will crunch it out for me. But I do not have a formula that tells me, I look at it and I'll know what it, I know how to figure it out without an algorithm. Champernowne, though, set out to find a number which was normal in base 10. To engineer a number is easy. To verify that it is an existing number is normal is hard. Mostly because for numbers like square root 2, e, pi, we know what their definitions are, but we do not have a refined enough knowledge about their digit expansions. That's where the hurdle is. Creating numbers which obey certain properties is an easier task. And that's what Champernowne did. That's what Koblet and Nehru did.
There is one from Aman Sophie. Is it perhaps that Borel makes use of AC in his theorem?
I'm sorry.
Is it perhaps that Borel makes use of AC in his theorem?
Oh, that's what the question was, not to my knowledge. So AC is axiom of choice, I'm guessing, and the answer is no.
Any more questions? There are no further questions. Let's give the speaker one big round of applause.
Thank you for being such a great audience. We have had a lovely time.
Please join us over coffee, and the next Kaapi with Curiosity lecture is in January 25th, the day before Republic Day. It's on quantum mechanics, the wild world of atoms. So please visit us. Thank you.